Hey there, welcome back. It is a beautiful snowy day here in Utah. It's February, and so I'm not used to seeing this much snow, but I like the snowy weather, and we live in a desert in Utah, so I'll take whatever moisture we can get. We need it for the summer. This is a lecture that has been under popular demand for quite some time. And I've had on my channel previous lectures that introduce this topic of seismic building codes. But the building codes have undergone some really significant changes since, frankly, 2016. And then they went into effect in 2018 and were adopted in 2019, and then it felt like the whole world was flipped on its head. And so I've been working a lot with consulting engineers in practice on this topic of developing ground motions for seismic building codes, and that's really what we're talking about in this lecture, is developing the design ground motions that you would use in building code compatible with international building code or with ASCE 7. So, by way of introduction, most of these modern seismic building codes, they've undergone a lot of significant changes. So the changes I referenced, those aren't the first time that there's been some big changes. The codes have been regularly updated about every 6 years. Beginning in 1996. And these changes relate to how design ground motions are obtained. So how we want to develop the motions that engineers are going to use to design their buildings with. So just so you understand what you're getting into with this lecture, this is a geotechnical class. So I'm not going to dive into any of the structural design beyond some of the basics of structural design class, SDC, or seismic design class, excuse me. Everything else is going to focus solely on the ground motions themselves. So let's dive into a little bit and just talk about some of the basics here. When we talk about seismic building codes, and we talk about ground motions, there's currently only two ground motions really that we consider. There's what's called the maximum considered earthquake, or the MCE. So whenever you hear engineers say MCE, that's what they're referring to, is maximum considered earthquake. And that really is intended to be kind of like the apocalypse event, the doomsday event, the really, really bad earthquake. And maybe that sounds dramatic, but that's the spirit of what the MCE is supposed to be. And then the design earthquake, or the DE. And the design earthquake is the everyday earthquake. It's the earthquake that we're trying to design to keep our building from tipping over. And so the design earthquake is the earthquake ground motion that the structural engineers will actually use in the majority of the design. But for certain things and certain structures, they might refer to using the MCE ground motion instead. I should also point out that when we talk about MCE and DE, these refer to specific codes like IBC, ASCE 7, and NEHRP, National Earthquake Hazards Reduction Program, NEHRP. These terms, MCE, DE, they appear in these codes. Now, there's other seismic codes, like for instance, AASHTO has a code for the seismic design of bridges, but it's different than for buildings, and so they don't use the same terminology like MCE or DE. There's a lot of similarities, but there's a lot of differences. So everything in this lesson is going to be all of these building codes. and I'm not going to be referring to the bridge codes like in ASCE. But with the stuff you'll learn in this lecture, you'll be well armed and prepared that if you delve into ASCE, it's not a difficult leap. So in this lecture, I'm going to use references and images from the most recent version of ASCE 7, which is ASCE 7.16. The 16 refers to the year in which the update occurs. So this was updated in 2016, and it's the basis of the most recent IBC, which was IBC 2018. And so these codes are going to change again. It's anticipated this every 6 years it changes. So the next code revision will be 722. And so I'm going to have to delete this lecture again sometime and refilm it and give you the updated code. But the one thing that all these code updates have in common is they follow the similar progression. And the progression goes something like this. So there's a committee, it's a pretty prestigious committee, comprised of mostly structural seismic engineers, but there's also a few geotechnical engineers, a couple seismologists on there, a couple building safety experts, but they comprise the Building Seismic Safety Committee, that's the BSSC. Now, that committee meets regularly, but they will meet to discuss the changes they want to implement in building code. And they'll debate that. They have this entire process of vetting, debating, getting comments back, and that process lasts about 1 year. After that 1 year, and they have everything they want to do, they do a test run in a very experimental building code, which is the NEHRP code. And so the NEHRP code is kind of where, think of it like the beta code. It's where building code is sent to be tested and to see how it's received and to see what kind of comments it gets. I'm not aware of any municipalities, cities, governments, or anything that actually designs to NEHRP, but the current NEHRP code is the future of the building code. So after it's been in NEHRP for a year and comments are received, it gets published in the ASCE 7 code. Now, bear in mind that that happens every 6 years. So this committee meets also about every 6 years. And so it's going to meet about 2 years before the ASCE 7 update is put out. So the BSSC, therefore, is in the process, they met last year in 2020, and NEHRP should be getting published this year in 2021, all in time for ASCE 722 to be published. And then ASCE 722 is going to stick around for 2 years and get feedback and get tested and tried until finally it will land into the International Building Code, or IBC. And this is where now, this is the code that kind of rules them all. This is the code that engineers will predominantly use to design commercial, large residential, industrial buildings of that nature. So let's talk a little bit about what I call old code versus new code. And that's because old code is the code that was around when I entered the profession. And so that's the code that you kind of grow the most fondest of. And boy, I have fond memories of that code, because compared to the code today, that code was really simple. The old code, so this might be ASCE 705, IBC 2008, 2009, etc. The ground motions were developed using some really simple rules. It was used using a uniform hazard approach. So uniform hazard, we talked about that in the probabilistic seismic hazard analysis lecture, and we'll talk about it again in the conditional mean spectrum lecture that's coming up. And so the idea with uniform hazard is that if I have a response spectrum, let's get rid of this old figure. If I have a response spectrum that has period in seconds, spectral acceleration on the y-axis, and I have some response spectrum that looks like this, each one of these points along this spectrum corresponds to a different period. A different period of vibration, and so on and so forth. And the idea is that in a uniform hazard spectrum, each one of these corresponds to the same return period. So in this one, the return period of spectral acceleration 5 is, I don't know, for this one we could say, whoops, I'm sorry, that's the mean annual rate of exceedance. It might be 2475 years. It could be something else. I'm just using that number. And in this case, the return period of spectral acceleration 4 is the same likelihood. And this is spectral acceleration 3, so the return period of spectral acceleration 3 is 2475 years, on and on and on. And so every point on that response spectrum corresponds to the exact same return period. And I'll discuss why in the conditional mean spectrum lecture, why this is what I refer to as Franken spectra. I claim the copyright to that name because I think it's cool. It's a scary spectrum because it doesn't really represent any real earthquake. It's kind of like a nightmare spectrum. And so the old code used it. And the MCE corresponded to those spectral acceleration values that at that return period of 2,475 years, which also corresponds to a 2% probability of exceedance in 50 years. And the design earthquake corresponded to just a fudge factor times the MCE. It was a reduction of the MCE, and it was a uniform reduction of 2/3 or 67%. And so I won't get into the politics of why 2/3 and where that came from. There's lots of disagreement on where that came from, and I have my version of the story, and so I'm not going to waste your time with that. But needless to say, the code has now codified that 2/3 of MCE is the design earthquake. And that's how it used to be. I mean, it was simple. You would perform or the USGS, the U.S. Geological Survey, would perform a PSHA, and then they would grab the return period of 2475 years, and then they would just map it across the U.S., and we would get these seismic hazard maps, and that was it. So you would just go to the seismic hazard map, get your 2475 year ground motion, you would adjust it for your local site effects, site response, for example, and then you just run with it. Now, the new code, it gets a lot more fun. In the new code, they wanted to move away from Franken spectra. And what they wanted to do is they wanted to, instead of focusing on a likelihood of the ground motion occurring, they wanted to focus on the likelihood that the structure collapses. And ultimately, that's what we're after, right? We're after the performance of the structure, not necessarily the occurrence or the likelihood of the ground motion occurring. And so this type of approach, where we focus on the performance of the structure rather than just the likelihood of the ground motion, is called a risk-targeted approach, or sometimes it's called a performance-based approach. And performance-based is a topic or an area of expertise that I've focused a lot of my research in over the past 16 years or so, and so but in the geotechnical engineering arena. So again, everything we're talking about here is structural engineering, right? So ASCE 716 and IBC 2018, while those codes already had now the risk-targeted structural components, they were still based on some pretty old and archaic geotechnical components from the old code back in like ASCE 7-5. And so in 2016 in ASCE 7 and 2018 for IBC, the BSSC introduced some major changes to the geotechnical aspect of developing these ground motions. And really, that's what this lesson is all about, is developing the ground motions now using these revised approaches. So, like I said, in my old lectures, this used to be 2 lectures where one just focused on the general approach, and then the second lecture I presented a site-specific approach. Now I've combined both those lectures into one lecture here. And why is that? Well, because the site-specific approach just got too complicated for an introductory earthquake course like this. And so I don't talk about it in much detail, but we will talk about it a little bit. So let's try to cover as many of the basics in the new code as we can today. So what I've done is I've taken the liberty of just taking a whole bunch of verbatim language right out of the codes. To me, that's the safest bet, because that way I don't paraphrase and screw something up and then get sued by somebody who heard me and didn't follow the code instead. So here we go. Let's just read. This is from ASCE 716, from Chapter 21, Section 2, Part 1. And it's about probabilistic, MCER, and this little subscript R means risk targeted. I'll put that right here. All right. The probabilistic spectral response accelerations, so that's the response spectrum, shall be taken as the spectral response acceleration in the direction of maximum horizontal response. So that's one thing that was new. Represented by a 5% damped acceleration response spectrum that is expected to achieve a 1% probability of collapse within a 50-year period. So the 2 new things that appeared that weren't in the code before is first this direction of maximum horizontal response, and the second, the compatible spectrum that is expected to achieve a 1% probability of collapse within a 50-year period. Now, collapse of what, you might be asking? Is this a collapse of a steel building, collapse of a concrete building? What is it? And I've asked this question, and the answer that I received was this is a generic reinforced concrete structure. And that's it. That's the answer I've received from the experts who wrote the code, and I don't know any more than that. And I suspect that future versions of the code will have provisions for different types of structures, but for now we're just focusing on a generic structure. And so let's just take a moment and talk a little bit about what it means when I say direction of maximum horizontal response. Let's go back to the whiteboard. Hopefully this will be helpful to you. So let's just say I'm looking at a map of the state of Utah, and right in this location here I have a ground motion recording instrument. And if I'm looking in plan view, the ground motion recording instrument has a component that points one direction. It has a component that points in the other direction 90 degrees from the first, and then it has a component that goes in and out of the page. And so this would be a typical 6 degree of freedom instrument. So it can record motions, 2 horizontal and 1 vertical. Now, depending on the orientation of the fault and the way that these things are recorded, if I were to look at the response spectrum from, say, the north-south horizontal component, I might get a response spectrum that looks like this. And let's say I look at the east-west component, the one that's orthogonal to it. I might get a response spectrum that looks like this. They're going to be different, and that's because the waves are dependent upon the orientation of the waves, and the orientation of the instruments recording them. So different orientations have different responses. So the question, the $1 million question is, which orientation gives me the maximum peak response? Is it this orientation here? Is it this orientation here? Is it this orientation here? The point is, we can't have an instrument in every orientation. So what we can do, as long as we have these 2 orthogonal directions, we can use math and what we know about polar mathematics, and we can rotate those 2 vectors essentially 180 degrees, and we can rotate and we can fill the entire circumference of ground motions and get the maximum or the minimum, and find out what that maximum orientation is. So the code is now telling us specifically, hey, you need to use the maximum horizontal response. And so to do that, we generally have to apply a fudge factor to whatever median response we're computing from our NGA equations. That's right. NGA, attenuation relationships, those do not give us the max. Those give us the median, or kind of think of it as an average. Okay, so we got to not use those. We have to want to use the maximum. So you'll take the median response you get from your ground motion prediction equation, and you'll apply a fudge factor to get the maximum response. Okay, but now let's focus more again on this probability of collapse. So when we see this, the code now is obviously more concerned about the consequences of the ground motions than the ground motions themselves. Make sense? All right, I've got to throw a bone to my good friend and mentor, Dr. Zia Zafir. He works for the consulting firm Kleinfelder in Sacramento, California, and he's a good friend. And he shared with me this flowchart, and I really liked it, and so I'm stealing it with his blessing and sharing it with you, because this flowchart is a decision chart that really guides one through this process of developing ground motions using the ASCE 716 or the IBC 2018 approach. Now, for those in my class, don't hyperventilate when you see this flowchart, because again, this is just an introduction. I don't expect you guys to master this. But when you get out into your practice, you're going to need to use this approach. And so it's important that you get exposed to it early on and ask your questions now rather than later when you're expected to perform. So if we just walk through this quickly, basically the first step is you got to look and see if you have a site class F. And a site class F means, and there's some very specific requirements that we'll discuss, but it basically means you have, you have tricky soil. Okay, so if you have tricky soil, then if the answer is yes, and you have, then you can see the next question relates to the period of the building. Is the period of the building less than half a second, or is the period of the building greater than half a second? If the period is less than half a second, that means that we have a short period building on long or high period soil. So the building is going to be out of tune with the soil, and we can go back to some of the more generic code-based approaches. But if I have a high period building and site class F, this tricky soil is generally high period soil, it's possible that my building and my soil are in tune. And if that's the case, I need to do a site-specific approach. And that's no small task, believe me. That's probably anywhere between a $10,000 to $30,000 engineering analysis to have those ground motions developed, at least if they're done right. Okay, but let's say if you don't have tricky soil, you have more conventional soil, you have a site class D or an E, then there's some other triggers. They do have a short period trigger, but the short period trigger, it doesn't really apply to any realistic place. But the one trigger that gets everybody is this one. There's the spectral acceleration at a period of 1 second. That's what this S1 means. It's the value from the response spectrum at a period of 1 second. Is it greater than 0.2 Gs? And that happens a lot. And if it is, then we have some choices. Basically, it's saying you have to do a site-specific ground motion hazard analysis, unless you don't want to. If you don't want to, you can look at the exceptions that you have, and if you have any of the exceptions, you might be able to get out of it and still go back to this generic code-based approach, which is easier to perform, but you're going to design to larger ground motions, so it's going to have more expense for your actual structure. So hopefully just this little flow chart here gives you an idea of the flow of decisions that you would make in developing ground motions for design. So let's look at step one. First, you have to determine your site class. And site class is a function of the soil that you have. Soft soils, or very, very deep and soft soils, are generally going to have higher site classes, site class E, site class Fs. Stiff soils are going to have lower site classes, site class C, site class D. Site class D is kind of considered the generic soil, typical soil, and so a lot of people just assume that that's the default site class. At least the old code allowed you to do that, but the new code doesn't really allow you to do that. So here we are in a table in the code, and you can determine site class one of different ways. If you measure the average shear wave velocity of the site, then you are able to determine the site class. Okay, now which average shear wave velocity do we talk about? Now remember, we're not talking about the arithmetic mean, but we're talking about a harmonic mean. And it's computed a little bit differently than we would with the arithmetic. And in my 341 class, those who took it from me had some exposure to computing harmonic means. Now, if we didn't measure the average shear wave velocity, we could base it on average SPT blow count. You can see here for site class C, D, and E, we can just use this range of SPT blow counts to approximate that. Why not A and B? Well, because A and B are rock. You can't do a standard penetration test in rock. That doesn't make sense. By the way, in future revisions of the code, using SPT blow count, it's going to go away. So enjoy it while you've got it, because pretty soon it won't be here. And the same is true with using undrained shear strength. The average undrained shear strength for the soil column in the upper 100 feet, again, computed using a harmonic mean. But, again, here's the ranges that we'd use for site class C, D, and E. The point being that you are now going to get, you're going to define whatever your site class is. Now, there's special consideration here for site class F, and you can see that says soils requiring site response analysis, and that's because they're tricky soils. So site class F is any site that meets the criteria that are laid out here. So, for instance, it would be soils vulnerable to potential failure or collapse under seismic loading. So that might be soils that are liquefiable soils, quick soils, or highly sensitive soils, or collapsible or weakly cemented soils. Anything like that where an earthquake might cause collapse and large deformations, yeah, we're worried about that. And so we're going to call that a site class F. However, you'll notice that for each one of these there's exceptions. So for that first rule, you have an exception if the period of your structure is equal to or less than 0.5 seconds. And again, the reason for that, if we go back to the whiteboard, is pretty simple. I don't want to draw red. Let's draw with black. There we go. All right, so if I have a site class F and I have my acceleration response spectrum, a site class F might look something like this, where it has an amplified acceleration or amplified response spectrum at higher periods. And the point is, if I have a short period structure, so something that's like 0.5 seconds or less, you can see that this amplification out here in the higher periods doesn't really affect my structure in this zone right here in the short period. And so that's the reason for that exception for those long period, or I'm sorry, for those long period soils or short period structures. Okay, the second reason I would have site class F is if I have organic soils, so peats or highly organic clays. And notice with each one of these, it has a thickness criterion if you have more than 10 feet of it. Except, by the way, liquefiable soils. That's still a question. You notice there's no thickness criterion established, and that's because there's evidence that even very thin layers, like a foot or 2 feet of liquefiable soil, can dramatically change the ground motion properties that occur at a site. So the jury's still out on that, but as far as peats and highly organic soils, if you have more than 10 feet of that in your soil profile, you have a site class F. If you have very high plasticity clays, and it's greater than 25 feet in thickness, and your plasticity index is greater than 75%, then you have a site class F. Otherwise, you have a site class D or E. And then here's the exception here for this. Site response analysis is not required for this clay category, provided that both of the following requirements are satisfied. First, if the amplification coefficients, FA and FV, those are for short period and long period respectively, obtained from tables 11.4-1, 11.4-2, for site class D or E, multiplied by a factor that varies linearly from 1 for a PI of 75 to 1.3 for PI of 125, and is equal to 1.3 for PI greater than 125. And the resulting values of your design short period response spectrum acceleration and your long period design spectral acceleration obtained using those scaled factors do not exceed the upper bound values for seismic design category B. So these are very technical and very specific. Don't worry too much about it. If you ever get into doing this for money, you'll obviously dive into what all this means. But for the time being, just understand there is an exception to this, but it comes at a cost, so to speak, because what these exceptions are requiring you to do is to artificially beef up your ground motions for design, to be conservative. The last category for Site Class F is very thick, soft, or medium stiff clays. So by very thick, it defines it as thicker than 120 feet or 37 meters. And it tells you, again, you can see the average shear strength, undrained shear strength is less than 1,000 PSF. So that's some pretty goopy stuff. And there's another exception, a technical exception with that. We won't focus too much on that. But that's how we get our Site Class F. So here's the moral of the story. If you have a Site Class F, hang up your phone or put your computer away, put all your analysis away and your code away, pick up the phone and call a seismic geotechnical specialist, and they will help you determine the right type of analysis to help you with your Site Class F. This is something that the generic geotechnical engineer is not going to be qualified to do. It has to be a seismic geotechnical expert, and they'll know what to do. The price tag for this, again, is going to vary anywhere between $10,000 to $30,000 in general to get your ground motions if you have a Site Class F site. Okay, step number 2, you need to obtain your ground motion parameters S sub S and S sub 1 from the MCER ground motion maps. So again, in the old days, you used to be able to just go and get the uniform hazard MCE ground motions from the maps and you were good. But now it has to be modified for your risk targeted stuff. And so you're going to go to the maps. Fortunately, people have already done that work for you, so you can go to those maps and get your short period spectral acceleration and your long period spectral acceleration from those maps. So you can try to use microscopic vision and look at the maps published in the ASCE and IBC codes. That's going to require that you zoom in with your eyeballs and decipher some very fine contours. But the rest of us, we usually use a third-party website. So one website that's really useful and free is the SEOC tool. SEOC stands for Structural Engineers Association of California. And you can find that at just going to the website seismicmaps.org. Very, very useful stuff. ASCE has a tool as well, but it's subscription-based. It costs money. So what is S sub S and S sub 1, you may ask? Well, S sub S is the risk-targeted spectral acceleration that corresponds to a period of 0.2 second for bedrock material. Everything here is bedrock, okay? It's a generic type of material. S sub 1, this is the risk-targeted spectral acceleration at a period of 1 second. So this is the 1 second spectral acceleration from our response spectrum that corresponds to bedrock. And by risk-targeted, these mean that for bedrock, these correspond to a 1% probability of collapse of our generic reinforced concrete structure. That's what that risk targeted means. Okay. So, what about assuming geotechnical properties? What if we don't know? Now, in the old code, there were code provisions in there that allowed structural engineers to make assumptions about the soil without even doing any soil exploration. And fortunately, most of those have been removed in the new code because, frankly, they were a little dangerous. But here's what the new code says. Based on the site soil properties, the site shall be classified as a site class A, B, C, D, E, or F in accordance with what we just reviewed in Chapter 20. Now here's the kicker. Where the soil properties are not known in sufficient detail to determine the site class, aka no geotechnical engineer actually was hired or looked into the soil to define it properly, site class D may be used. But here's what was added in red. It must be subject to the requirements of section 11.4.4, which means you can't just get a free lunch anymore. You can't just assign a site class D and run with it. If you're going to just assign a site class D knowing nothing about the actual soils of the site, there's going to be a penalty. And if that's the case, then it's going to tell you right here in section 11.4.4 that if you're going to use site class D as the default, then the short period spectral response shall not be less than 1.2 times S sub S. So basically, you're jacking up your ground motions by 20% as an effective penalty, honestly. So this is going to increase all of your design ground motions. So by increasing your ground motions, it's like accepting a penalty for guessing what the soil conditions are. And very few engineers that I know do this anymore because that penalty is so onerous. Okay, so here we are. We're back at our flow chart. We've determined our site class. And so now we have to look at these different questions related to ground motions, the S sub 1 ground motions in particular. Let's look at this portion of the flow chart here. And let's say no. So let's say we have a site class D or E, but the spectral acceleration at a 1 second period is less than 0.2 g. What then? If that's the case, we can do a generic development of ground motion. So this is called the generic or the general code procedure. So if that's the case, you're in a great place. It's easy. All you're going to do, your next step, you're going to grab your site response coefficients or your site amplification coefficients, FA and FV. These values, FA and FV, are what effectively transform the bedrock ground motions to ground motions on the top of the soil. And so think of these as transform functions to convert bedrock motions to soil motions. The FA corresponds to the S sub S ground motion, and the FV corresponds to the S1 ground motion. Okay, that's why we call it short period and a long period. Perfect. So you'll just go to these tables, 11.4-1, 11.4-2. It's a function of your site class, and it's also a function of whatever your mapped spectral accelerations were at the short and long periods, respectively. Okay. Now, anything that has this superscript here, A, all of those basically mean you need to do a site-specific procedure. So all this idea or hopes that you're going to do a general code procedure, they're dashed. You can't do that anymore with the new code. So only if you are in essentially this region here and this region here can you really perform this generalized code procedure. Everything else is going to require a site-specific approach, which we'll talk about in a little bit. But assuming you're in one of those regions on those tables, you can move on to step 4. Once you have your FA and your FV parameters, you're going to compute the risk-targeted maximum considered earthquake response acceleration parameters. Those are called SMS and SM1. The M in there is MCE. So all this is you're just going to multiply the bedrock spectral accelerations you got from the maps by their corresponding site coefficients, FA and FV respectively. And that's how you get SMS and SM1. Okay? And those correspond to MCE ground motions. Then you also need to design ground motions. So to get the design ground motions, you're just going to take those values that you just computed, SMS and SM1, and you're going to multiply each of them by a factor of 2/3 respectively to get the SDS and SD1 ground motions. Now these are the design short period and long period ground motions that you would use. And the structural engineers would use these for their design. Then in step 6, you need to develop the various period parameters so that you can draw a response spectrum. And there's different period values. There's the fundamental period of the structure that we just call T. There's T naught, which is equal to this equation right here. You'll see what that is as soon as I show you the plot. There's the short period T, and then there's the long period T. There's the long period transition. So rather than try to explain these, just look at the figure here and you'll see what they are. So T naught is the beginning of this tabletop portion of the response spectrum. TS is the end of the tabletop period. And then you have this logarithmic decrement. It just decays at a nice logarithmic pace. And then you have a change in the logarithmic decrement for very long period stuff that occurs at period TL. So those are what the different periods mean. Okay. And the T, by the way, is just whatever period you're interested. Think of it, if you're plotting a function, it's whatever value of x that you're putting in to get the y value. Okay, so all of the response spectra for this generalized procedure, it gives you this flat top, tabletop looking response spectrum. And the whole purpose of that is to it's intended to be a conservative boundary or an envelope or a shell that encompasses and covers the actual response spectrum that you would get from an earthquake. So it's intended to be conservative. It's intended to be quote-unquote safe. Once you have that, then the next step is you need to decide what type of occupancy your structure has. So you're going to select the occupancy category. Some codes call it the risk category. So structures that have very low risk to its occupants, this would be like a tool shed or a garage or something like that, you might assign it a risk category or an occupancy category 1. So it has a very low risk to human life. And it won't really affect society if it collapses and fails. Now, contrast that with a risk category 4. This is something that is deemed an essential facility for society. So things that are essential facilities, they might include but are not limited to, and notice everything here has to do with hazardous substances, right? Anything that manufactures, processes, handles, stores, uses, or disposes of hazardous substances. And so it's interesting that that's what they focus on here. But it will also include structures like fire stations, police stations, things like that that are crucial to the functioning of society. Believe it or not, a lot of people, when I ask, give me an example of something that's a category, risk category 4, a lot of students will say hospitals. And the truth is, nope. The code says hospital is not risk category 4, but a risk category 3. That's kind of interesting when you think about it. I didn't make the code, so don't ask me about it, but that's just what it is. Okay, once you have your occupancy or risk category, then you need to define the seismic design category, or the SDC. The seismic design category is going to be used by the structural engineer to define all of the procedures used for the seismic design of the structure. So there's some instructions written here that you can read of how to determine that seismic design category. Basically, I like to think of it just simply as this. You have these two tables, 11.6-1, 11.6-2. You have your design ground motions here, your short period, and your long period ground motions down here in this table. You know your risk category. It's either 1, 2, or 3, or a 4. And from each one of these tables, you pick the one letter that corresponds to your category. And then depending on whichever one you pick, it's going to be the worst case of the two. So the highest letter is going to be the one that governs your design, and it's going to be your seismic design category. So in general, we go from A to D, and in increasing letter order, that is increasing seismic risk. So a seismic design category D is a structure that has considerable seismic risk and will therefore have considerable design requirements that it needs to meet. A seismic design category A has very little seismic risk and therefore will have almost no detailing, structural detailing related to seismic resistant design. So I think I laid this out there, that SDC, it's the one single parameter that the structural engineer will use to define the rest of the seismic design for the structure. Okay, that again is if you're lucky enough to be in this category right there for code-based design. Anybody or their grandma can do that stuff, okay? It takes a little bit of practice, but you'll figure it out, and it's very easy. But what if the answer to our question that we asked earlier for our example site is yes? What if our long period risk-targeted spectral acceleration is greater than 0.2 g, and I have a site class D or E? Well, now we're into site-specific analysis territory. And this is where I'm going to spare you the details, because this is where you want to have somebody working on your project who has a lot of experience and training in this. And by experience and training, I'm not just talking taking a class like my 545 class. To learn this type of analysis and to learn the nuances and to be able to spot the problems, it requires years of training, almost like in an apprenticeship role, under somebody who has that experience and can teach you the ways. So it really involves an apprenticeship. For me, my mentor, my trainer in these areas was Dr. Zia Zafir. I worked under him for almost 6 years at Kleinfelder, and we had a great relationship. But I learned a ton working under him for these site-specific things, these site-specific approaches. The danger that I see today, because this is now codified, is I see so many engineers who have had no training, no apprenticeship, they haven't even had a class, and yet they're claiming expertise in doing these site-specific approaches, and it's leading to some really wacky stuff in terms of ground motions being recommended for design. I hope that there's going to be some resolution there and that some safeguards can be put in place, because I personally am seeing some pretty wacky stuff happening in the world, in the geotechnical community right now in the United States with regards to site-specific hazard analysis. But anyway, let's jump back. I'm digressing here. In beginning here in ASCE 716, that the BSSC put in some pretty strict triggers on when a site-specific geoseismic approach needs to be performed. And the two types, when I say site-specific, there's really two types of analyses that I'm referring to, and they're different. They're not the same. The first analysis is what's called a site response analysis. And this is where we're going to account for how the soil is going to amplify or de-amplify the bedrock ground motions. That's all a site response analysis is. The second is a ground motion hazard analysis. So this is a site-specific PSHA and DSHA, similar to what you guys learned about in the seismic hazard analysis lessons. And as you're aware now, if you watch those lessons, this is no small feat. It is a major analysis. And so both of these need to be performed on a site-specific basis. Now, the code allows engineers to claim exceptions that would put them back into the general code procedure category. But there's usually what I term, and again, this is my term, a cost associated with that. And that cost is in forms of increased seismic demand. So sure, we'll let you go back to that general procedure, but you're going to have to jack up your design ground motions in order to do that. And if the engineer is okay doing that and designing to higher seismic demand, then that's fine. The code allows them to do that. But if they don't want to have that jacked up seismic demand, then they need to do a site-specific approach. So here's the exceptions to getting out of doing a site-specific site response analysis. And this is from section 20.3.1 of ASCE 7. Okay. Here's the exceptions down here. So, basically the site response analysis is required when you have site class F soils. And we already talked a little bit about these. And like I mentioned earlier, they are technical in nature. So the first, of course, is if the period of the structure is less than half a second. So this would be like a short, stiff structure. A structure maybe 4 stories and or shorter, very stiff, and you have liquefiable soils or soils that are prone to failure or collapse. If that's the case, you can claim an exception and get out of it and get back to doing a generic procedure with a penalty included. For high plasticity clays, we talked briefly about that exception, and then also for very thick and soft or medium stiff clays, a similar exception, a little more technical than I want to delve into for the purpose of this discussion, but there is an exception there. Now, if the code is requiring you not to do a site response analysis, but instead a ground motion hazard analysis, or a PSHA and DSHA, then there are some exceptions to that too. The ground motion hazard analysis is not required for structures other than seismically isolated structures. So if you're doing a base isolated structure, you don't have a choice. The code says you have to do a GMHA, the ground motion hazard analysis. Or if you have a structure that has an engineered damping system, you have to do a GMHA analysis. But if it's just a typical structure that is not base isolated or damped, then here are some exceptions. If your structure is on site class E soils and your short period risk-targeted spectral acceleration is greater than or equal to 1, provided that the site coefficient FA is taken as that of a site class C. So in other words, they're saying, okay, so you're on site class E soils, we'll let you take this exception as long as you make it so that your site amplification for the short period is equal to that of a site class C. Well, what that is it's a 20% increase. So that's the quote-unquote penalty or cost associated with that. Number 2, structures on site class D sites with a long period spectral acceleration greater than or equal to 0.2, provided that the value of the seismic response coefficient, C sub S, is determined by this equation for period values of less than 1.5 T sub S and is taken as 1.5 times the value computed in accordance for the periods past that. So in other words, what this looks like is, let's draw a generic response spectrum. So here's a code response spectrum, right? And it's basically saying that as long as you're here on this peak, anywhere, on the peak of that spectrum, you're fine. Go ahead and just design to that because you're designing to really high ground motions anyways. But then it's also saying if you're out here in this section with the logarithmic decrement, you have to stretch this out to a 50% increase and increase it by 50%. So now you're jacking up your ground motions by 50%, not just 20%. So you're designing to some pretty large ground motions. And then the third, structures on site class E sites with a long period spectral acceleration greater than or equal to 0.2, provided that the period is less than or equal to T sub S and the equivalent static force procedure is used for design. So that's a structural design procedure. It's intended to be very conservative. So again, all this is saying is if you're on the very top, the plateau of that, hey, you're fine. Go ahead and just stay on that plateau, but you have to use the equivalent static force procedure. So no matter what you're doing, there's going to be some conservatism there. So why do I call taking any of these exceptions a penalty? Well, for the site class E exception, those short period accelerations are going to be increased up to 20%. So you're increasing your ground motions by up to 20% for design. For the site class E exception with the long period greater than 0.2 G, you're going to be forced to use the peak of your response spectrum for design. So in other words, you're basically saying, well, regardless of what the actual period of my site is, I'm going to move my period over to the peak of the response spectrum, and I'm going to design to that. And those can be some very large ground motions. And if you have a site class D where your long period response spectral acceleration is greater than 0.2 G, you're going to increase your ground motions by 50%. Just to be conservative. So again, these are massive penalties. So I have some really good structural engineering friends who get upset with me when I use the terminology penalty, because it implies that they're being naughty if they choose to take these exceptions. And they say, why do you keep using the term penalty? And I sum it up like this. Basically, because I call it a penalty because I cannot think of a single, not one instance when accepting these exceptions, any of them, would produce a smaller seismic demand to use in structural design. And if you're going to jack up your design ground motions, then that is the equivalent of a penalty or a cost associated with the simplification in your analysis. So, for site class D and E soils, in moderate to high seismicity areas, you should always, from this point on, always plan on performing at least a site-specific ground motion hazard analysis, a PSHA or DSHA. It will lower the demand, it will reduce the cost to build your structure because your seismic demand will be reduced. Otherwise, you're going to pass on these costs to your client. They're going to have to pay for the increased cost to design a more rigorous structure for those inflated seismic demands. And I don't know too many clients who would be very happy with that. So this is where we are, folks. We're in a day and age now where site-specific ground motion hazard analysis and site-specific site response analysis are being required on everyday practical projects. So it's a good time to be an earthquake engineer. Lots of demand for our work. And I'm glad. I'm glad to see those moves made because honestly, as far as the science goes, it's the right call. We've known about these phenomena for decades now, and they're finally just moving into the building codes. So that's all I have for you in this lesson. I know there was a lot of technicalities there. Don't stress too much about it. You'll learn more about these when you get a mentor yourself, when you enter consulting and you become an earthquake engineer. But thanks again for watching, and I'll catch you in the next lecture.